Hello viewers, welcome to my channel Science to Technology. In today's show, Computer Wednesday, we're going to talk about cooling the modern AI beast. So let's dive deep into it. We have already talked about how to power these puppies. Let's talk about how to cool these puppies. Well, first law of thermodynamics is your main enemy. Energy cannot be created nor destroyed. What does that mean? That simply means same way our body is always generating heat. That's the same thing happens to a CPU, GPU, whatever have you, basically silicon. So all the energy that goes into it is just becomes raw heat. Like if it's a 600 watt GPU, it's a 600 watt room heater. There is no difference. Now, like what about sending signal out? So unless it's a dedicated optical chip where it's like, it's converting a lot of energy into photons and sending it through optical fiber, in most scenario, 99.99% of energy will be just radiated at heat. So your room heater and computer functionally has no difference. So that's the one thing. And because silicon die is so small, so compact, yeah, that can cook itself. That's a very hazardous issue. As in, if you do not leach heat away quickly enough, it can burn itself out. Now, thankfully, nowadays, modern silicon has enough engineering into it that first it will try to save itself by throttling it out. If it reaches like, yeah, I'm still hot, it shuts it down. Back in the day, people used to burn CPUs because of the failure in cooling. There was not enough engineering in the silicon itself as like, whoa, I'm getting too hot. It used to self-destruct too much. Now, again, it still happens once in a while, but it's much rare where it was like a common thing to like, okay, once in a while. It should not happen. In a good system, it should not happen. Now, temperature has a vector to it. For example, same way when you say energy, generally you need watt. Heat does not have something like that. So you have two vector like voltage and amps. You have degrees Celsius and heat flux, watt per meter square, basically how much oomph is there. Now, AI chip is bad in this regard, like horrifyingly bad, because again, it's millimeter square, so to say, a die, single die, and even the big ones. And they are hot, as in, again, we are reaching a point where we have literally trillions of transistor. Nuclear reactors core, like if you take a nuclear reactor core, they generally are under 200 watt per meter square. Yeah, that reactor was a huge, and you don't want them to be super duper high energy because again, it's not very stable for long term. And again, they don't want to make it turn on and forget about it for 15 years. So they work their ass off to keep it cool. But again, 200 watt per meter square is no joke. AI crosses 300. 300. It's bonkers. It's stupid. Again, because of the size. It's like the silicon size is huge. And again, you must have experience, especially with laptops. Like even in a thermal camera, you can see like the die could be much hotter, like 90, 95, and your outside keyboard would be 77 degrees Celsius. So that degree Celsius, that's one vector, that's voltage. Amps is basically how much heat is there. So we measure it by kilowatt hour. Yeah, in many designs, it can reach kilowatt. So this is a problematic aspect. Now, conductivity is the main essence that we are dealing with here. Heat does flow from hot to cold. That's good, but it's not magic. What does that mean? That simply means you have to do math. So there are two vectors that you have to apply. One is T delta, basically how hot is your hot, how cold is your cold. Cold in this scenario would be your room temperature. Hot would be how hot is your silicon or how hot you can allow the silicon to be. For example, server silicons, because they do not go on-off cycle, they are okay to keep at hotter temperature, meaning the package temperature or die temperature, because nowadays we have some thermocouple in the die itself. Those should be, let's say, 95. That's the upper limit. That's the T hot is fixed. Your T cold is relatively fixed unless you have an active cooling system. So these two things combined, basically T delta and thermal resistance, basically how hard it is to push the heat, that defines your operating budget. Meaning what happens if the budget is not done correctly, as in like a resistor, basically the interface point between your silicon and your heatsink is not great. Let's say you put too much thermal paste, or you did not put enough, or you had like did not remove the peel before use. You could reach a point where it's like, yeah, my CPU is supposed to be at 5 gigahertz. It barely runs at 3 simply because it's like, yeah, that resistor is limiting it because voltage has to go up in order to push through it. Can it push through it? Of course, but it will burn. So it's like, no. So these two things are defining factor, and metals are not that great because of the density required. Again, even for transistors, I'm making a lab bench power supply, so linear power supply. It has a what you call power MOSFETs, not MOSFET, BJT. Now it says very clearly, if the outside package is 100 degrees Celsius, that means the inside, as in the die itself, could be 125 degrees Celsius. So try your best to not let the package go too hot. So that's the one thing you have to understand. If, for example, let's say you have a CPU cooler, something like this, and you are saying, oh, you're touching the heat, oh, it's not that hot, does not mean that CPU is not cooking. It's already cooked, because the conduction, the resistance is so high that it can't push enough heat away. Meaning, to push heat till this point, it has to be very hot. For example, this sort of radiator can be used for LED, but be mindful, doing so will shorten the LED lifespan, because LED has to heat up much hotter, like 75, 85, 108. Only then it can push enough heat away. Otherwise, you might as well chop it here. It will make no difference. So this is the best example you have to say. Like, oh, I have this heat sink and all that. Yeah, only small portion of it would be used. You have a silicon die that's actually creating heat. It's dissipating, but because the silicon die cannot cook itself, should not cook itself, it can't be too hot. And resistance of solid copper, solid aluminum is not low enough. The resistors are not low enough. And not to mention, if you have some sort of dielectric, either by basically thermal paste, or in case of this mylar sheet, to make sure that electrically it does not short, that makes it worse. So fundamentally, you are limited, as in, like, even the best copper heatsink you can get, that's only 200 watt per meter Kelvin. Just don't focus on the number. 200 is not that great. Do we have a solid that is great? Yeah, it's called diamond. That puppy is 2000, but I'm reasonably sure you're not expecting to put a diamond heatsink. I'm not talking in like interface. The heatsink has to be made out of diamond for actual use case. So that's the issue. And without active systems, nowadays you can't cool your system. Flat out, we have crossed that threshold. Meaning, if you look into very old system or very low power system, you could find system that are just a heatsink. Like, you can buy some very cheap AMD. I have not seen AMD doing that, but you can still buy some Intel that is just aluminum block, no active system inside, just aluminum block and fin. Again, I'm not talking about fan as an active system. I'm talking about the cooling material itself. So there is a limit. Conductivity is a limited thing on a metal. Like, there is upper limit. You can't utilize it. You can't be like, okay, what if I put a 10 kilogram of radiator? It does not matter. Because to utilize that whole 10 kilogram of it, it has to be very hot. So your diesel engine can handle it. Diesel engine is like, bro, give me a radiator, because again, it can operate at 200, 300 or a boom at temperature of 400. It's like, bro, I'm fine. I can run air cooled. Yes, there are some diesel engines that are raw air cooled. Not joking. They were designed for a hot running environment like Sahara Desert. But your silicon is like, bro, I'm gonna burn and self-destruct long ago. So conductivity is the physical limit, and every resistive elements you have is a hurdle for you. For example, your CPU cooler is huge, your laptop cooler is not. But what if you want to use the same silicon budget, as in like 75 watt? What you do is throw away the heat spreader. And again, same heat source, but because you have thrown away one resistor, it becomes far more cooler. Then why do we have that resistor in your desktop? Because you are not designing the heat sink. As in, Intel sells you a CPU, AMD sells you the CPU. You are the one who puts the basically cooler on top. So if they give you bare die, it will be much better. Physically wise, it would be better. It's just problem is, you couldn't tighten it too much, crack. Silicon goes crack. That's not acceptable. And that's why when you look into GPUs, day one, they never had a heat spreader, because otherwise they will not physically be able to cool. So be mindful. Resistors, how many resistors are there? And conductivity, that's your upper limit. Can you brute force to utilize a conductor? Of course, but that means your T delta must go high. So this is the conductivity physical limit, like you cannot breach it, bypass it. So we utilize active system. So the idea is solid metal is basically one atom has to take so much energy and then bump into the next atom. It's like, oh, it has to do that, and it's a very heavy process. It's slow. So somebody figured out, what if instead of solid, what if we let liquid flow? Liquid is very flowy. So the idea is latent heat through phase change, basically boiling. For example, what is here? You have liquid, generally water, under low pressure. Let's be very clear. So it will boil, let's say, as very easily as 30 degrees Celsius. Some can be so low temperature pressure that it can boil at 10. Let's just say 30 degrees Celsius. It boils there. The liquid does not go above that temperature, boiling temperature. It just changes the phase. So it is liquid at 30, 31, it's gas. So that gas goes to this cold end. Cold end, it dumps, condenses, and that allows you to dump all the heat very quickly, and then the cycle repeats. Basically, there is an air conditioner running inside it. Exactly how you have your air conditioner is just running in a positive loop. Air conditioner forces in negative loop, as in like your inside becomes cooler than the outside. This just equilibrates it. So there is a liquid that is boiling, there is a liquid that is transporting, there is a liquid that is condensing, a vapor that is condensing, and that's continuing the loop. That's why copper rod versus copper heat pipe is like bam, done, rapid, done, go home. Like it's super duper hyper quick, and that's why you can never find any modern CPU cooler or even GPU cooler that does not have heat pipe. The idea is heat pipes takes the heat from your silicon, dissipates into all the fins. Fins directly is too resistive. This bypasses that. It gives basically, you can see that like in old AMD CPU, the CPU block is here. You have pipes going on the upper ends. Why? It's using that part of the fin that would be wasted. So it's taking that heat from here, instantaneously dumping it on the top end. So your T delta goes down, basically how hot the CPU has to be in order to utilize the whole system goes down. This is the only reason why we have GPUs and CPUs. If we had not developed this and made it cheap enough, nobody would use it. So, because again, it's a physical convection that is happening with actual gases, liquid moving around. So it's a very high capacity, very high capacity. And generally, based on your requirement, you will select the heat pipe. For example, you could use water. Most of the time, it's water. Sometimes you can use ammonia. Or if you are NASA working with, let's say, NASA kilowatt reactor, it would be sodium. Like, wait a minute, sodium is solid. Yeah, not nuclear temperature. At nuclear temperature, it's like, bro, me liquid. But some are mercury based also. Not popular anymore, but there used to be. So fundamentally, this is how it works. It's a full loop of refrigerant that is going around. Heat pipe, now heat pipe is single axis dimension, one rod. Vapor chamber is two axis. Basically, what if you want to spread the heat? For example, your smartphone. Your smartphone silicon is not that hot, as in like how many watts it has? Half a watt, quarter of a watt. Then why the heck it's so painful? Well, it's such a small area that is very, very difficult. Very difficult for it to burn all that heat away, dissipate it away. So we put vapor chambers. Vapor chambers simply spreads it out. So if you have a mobile phone and all it has like, let's say full size vapor chamber, it will cool down your silicon. You can have gaming mobile phones. That's why they have to have vapor chamber. They can't work without it. And again, you are not cooling it, you are just dissipating it. And penalty of dissipation, energy cannot be created or not dissipated. If this side and this side, bottom sides are of the same temperature, that means you leached heat away, meaning the CPU is much cooler. For example, let's say you are making PlayStation. So PlayStation has a silicon here, but because of the geometry and all that, you have this L-shaped heat sink. Now, generally you would think, hey, we have metal good. Yeah, it's not useful. Why? This has to be very hot for this side to become hot because of the resistance. So you have the metal, but it's not helping you cool the silicon. Silicon is still overheating. Now, somebody smart comes along. It's like, what if we put a layer of vapor chamber? Now, again, it's not a layer. It has to be engineered, but it can be done. It is done. You can buy it. And then you have heat here and it dissipates instantaneously, almost instantaneously, speed of sound, dissipates to this corner. So your silicon temperature goes down. Same amount of metal, and you are not doing anything more. You're literally cooling it down more simply because that liquid circulation that is happening is dissipating the heat. So all the aluminum fin are contributing equally. That's what you want. You don't want, oh, this fin is doing the heavy duty, this is not doing anything. No. If you have the aluminum fins or copper fins, you want to utilize that. And this is the reason why you have servers. Servers literally have a ginormous vapor chamber. And that vapor chamber is bonded to copper heatsink, giant heat sinks, and they have run a jet engine through it. That's how they can maintain it. So be mindful, without vapor chamber, high-end systems will simply not exist, flat out. Like, oh, you need a CPU cooler that is to you and you want to dissipate heat. Yeah, that's not happening without vapor chamber. Like, don't even try. Modern ones, you can buy some old CPU that is not that hot. Modern one will cook it, like Epic CPU, it will cook it. So this is active system. That's why we can actually manage modern systems. But we kind of crossed that threshold also because just so much heat that you can't dissipate in a chassis. It's no longer, okay, leaching the heat away, that part is done. It's just that your air has a conduction limit, meaning the surface area needed can't fit inside a server. So you have to take that heat away. Water is the best working fluid for that, and it can take concentrated heat. That's why we use it in our basically cars. It's very good for that, and it allows you to collect all the heat and dump into a location of your choosing. Generally, they are dumped into a heat exchanger. That heat exchanger is running by building cooling. So it gives you complete freedom. Even in your desktop system where you have like, cold plate that is trying to cool your CPU, that's not doing the work. The water is not doing the work there. Water is just a conductor. It's almost like a heat pipe, but far more slower, but far more cheaper and far more high throughput. It goes through radiator, radiator dumps it away. Radiator is like huge radiator, low airflow. So that's how it works. Be mindful, water is so good. All the coal power plants, nuclear power plants, they're turbo generator. Yeah, those turbo generator stator coils, they are cooled by distilled water. But be mindful, pure distilled water. And I mean pure distilled water. So you allow it, basically water gives you a isolation where it's like, generate the heat there, let me dump the heat here. That allows you to make much higher density system. And water block design, basically the radiator, that part is sorted. Like it's the same radiator that we have been using for aircraft, from cars, for everything. It's done, it's sorted. It's just that water block design defines how much heat you can dump into it. For example, in the old designs where they have just like, CNC, like, yeah, it's not good enough anymore. So what we do is potato peel it, go shh, shh, shh. And that allows us to make very thin, like this is big one, so you can see that. I've linked the video down below. So they skew very tiny fins into it. Again, Gigabyte, if I'm not mistaken, they're also trying to 3D print the damn thing. If you can make the cold plate better, because what is the limit? Water has a fixed temperature. Let's just say you have a very good cooling system, water will not go above 50 degrees Celsius. Okay, what is the temperature of your CPU? That depends how much resistance you have. Let's say everything else is fixed, right? You have a silicon die, thermal paste, heat spreader, then your basically thermal paste, then the cold plate. Now cold plate to liquid, that's the transition phase, noisy transition. You have solid and liquid, you have turbulence. Is the turbulence working in your favor or against you? If it's working against you, you will not get much cooling. But if it's working for you, you're going to get awesome cooling. Water temperature is same, but your CPU would be hotter if it's not efficient. So that resistor has to go down. So skewing was one of the very successful attempts. At low cost, this is still the king. Some companies are trying to 3D print it, as in like create a very unique, very intricate water flow pattern. That's like, I got this, I can handle it. But it does come with a side effect. They do block up and clog very easily. So your water has to be pure. And pure, I do not mean just like biological contaminants, also from salts and debris. Otherwise, they will jam up. So cold block is the limiting factor here. How cool can you make it? Now, water does come with this one tiny penalty that it is conductive the moment it gets some salt, which is everywhere. And so it's a very hard liquid to have. This is like from MSI. So it's like, okay, I need bunkers GPUs. Okay, how the heck you gonna pack it? You can't fly a jet engine there. It won't be able to cool. Again, air is not dense enough. So they're like, okay, water blocks. Okay, great. But how the heck you do so much wiring and plumbing? It's like, throw it away, have water manifold, and then have like slot connectors for the power, and PCI is already a connector. So you just drop this cassette, almost like, ka-chung, done. So that's how modern AI systems, where they're like, oh, we are reaching 40 kilowatt per rack. Somebody's trying to like 100 kilowatt per rack. Yeah, that's water only. At that point in time, it's like you will have a CPU that is fully flat, RAMs laid out. That's why NVIDIA's RAMs are not socketed. They are flat slot. They have to be, otherwise they will not be able to cool it. So everything will be flat and you just have liquid plate on it. And these connectors that allows you to connect and disconnect without a single drop of water leak. That's expensive. Water is a harder thing to do. That's why likelihood of you seeing this sort of thing in your household is zero. They are very expensive. So this is water cooling. This allowed us to have some breathing room. Heat pipes were great, but again, because it was limited by air, they're like, okay, let's go to water. Water allows us to collect all the heat in a centralized place, and then you can dump it wherever you want. So water became the next milestone. Yeah, that milestone has been crossed because somebody is smoking so much. They're like, what if we put 100 kilowatt in one server rack? Yeah, nothing. Water cannot do that. Not because water cannot do that, simply because your computer can't do that. For example, water blocks is the cool unit, right? Like you put it on your GPU, GPU is cold, everything awesome. What about the things around it? So fundamentally, other things also get hot. If you're dumping that sort of energy, even 1% of waste heat is bad enough that over time it will cook it. For example, the worst thing would be VRAMs. Again, that's why I made the last video. The VRAMs get heat up. RAM itself, I'm talking random access memory, they heat up. VRAM, basically voltage regulator module, those heat up. And not to mention, you are trying to nowadays 48 volt to 1.2 volt. Yeah, those puppy heat up. And then you have bridge ICs like PCI retimer chips and networking chips, all of those heat up. So this whole idea is like, okay, I'm gonna cool the CPU and GPU, great, but other things also need cooling. So the whole idea is like, as you increase the electrical density, the raw watt heater, at some point it's just like dunk this puppy into liquid. And what liquid? Now, technically you can do this with distilled water. That's why I said turbo generators are done, but it's not viable. Like in few minutes, some dirt or contamination will leach into it, and the end, everything goes kaboom. So fundamentally, you need a liquid that is dielectric, basically like how your transformers are. Transformers also have the same problem. It's like they have very high voltage. From their point of view, this voltage is like, brah, you are below 50 volt. I deal in 50 kilovolt. So you have oils there, but problem is oil is very high temperature. As in, oil is just conducting, it's not boiling. They're not supposed to boil. But if you want temperature to be limited, locked, let's say 50 degrees Celsius, your liquid must boil at 50 degrees Celsius. Ta-da! That's the special sauce. Now, you need something that is low boiling point. You need something that is dielectric, as in electricity should not short on it, and then it has to be compatible with everything, including human, because human operator will touch it. It must be safe in all these vectors. There are only 2 to 3 chemistry formulation I have seen, and they are expensive as hell, and not to mention top secret beyond top secret. And this is not top secret as in like patent top secret. This is like, no, we're not gonna tell you how the heck we made it. So that's the sauce. Again, there are some designs I have heard, some chemical formulations, but chemistry is not my jam. So low boiling point, dielectric, 50 degrees Celsius. Why 50? Well, the idea is you dunk the everything. Let's say VRAMs are below 50. Liquid is circulating around it. It's fully submerged, so it's at equilibrium. CPU dumps heat. Temperature goes above 50. Water boils, and then the liquid boils. It turns into steam. It goes away. New fresh liquid comes in, it does the same thing. And because it's a physical leaching of energy, the temperature of the die does not even exceed like 60 or 70 degrees Celsius. It all remains in the reasonable system. And generally on top of this bathtub, you have a radiator. That radiator runs your refrigerant, as in your coolant from your building cooling. And that allows it to condense and it rains back. So again, you're not spending it, you're not letting it expand. It does work, that's the good part. And again, this was like always thought of, but it was not necessary. As in, like, you can find old videos of this sort of concept like 5 years ago, 10 years ago. It was just not necessary. Now it's becoming like, yeah, we have to do this. Like if everybody smokes and it's like, we need 100 kilowatt, and some are saying like, what if we push 200? It's like, yeah, air cannot do that. Like your motherboard will physically burn if you do that. So again, VRAMs also have some amount of waste heat. Look into your motherboard, like how big of a heatsink they put on the VRAMs. They are huge, they are hot. So, and everything heats up, right? And this has the two major advantage. Everything is cooled, that's the first thing, and nothing will exceed in temperature. That's the best longevity thing you are gonna get. Everything remains at 50 degrees Celsius, and low noise. Because you're not having fighter jet engines going on it, it's much cooler. And like, wouldn't it sound like a rain? Yes, it will sound like you are next to a river stream that is rocky. It's noisy, it's like shh, it's so much water droplets happening, but far more manageable, far more. And again, if you want to, if like you really want it to be quiet, you can do that condensation phase, like have a tube that goes into some place, a fan sucks it there. There you have a condenser unit, like shell in tube condenser, voila. You can do it outside, and then you can insulate that sound point. At that point, it won't even make sound. So very good for your hearing, very good for, again, it is expensive liquid, let that be very clear. Like you could be looking at $1,000 per liter. Again, for you and I, not for the companies. Companies gonna buy gigaliters of it, so I'm pretty sure it would be cheaper. But again, if you know the special sauce, human safe, dielectric, must boil at low temperature, and should not be poisonous to earth or to us. So yeah, that would be cool. So this is the future. We have to. If everybody wants to add bonkers amount of power, this is the only way to handle it. So this was my presentation on basically how the heck we are taming these beasts that we are creating. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excitement. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.